All right, the last video we were talking about the Sloan Digital Sky Survey. The thing about this that's important, of course, is that it maps this huge portion of the sky and is measuring, red shifts to galaxies. It's just devoted to this night after night after night for years, and so that we can accumulate tremendous amounts of data from this relatively inexpensive, when you compare like just to launch something into space, a space telescope. This is a very inexpensive method of learning about the universe. All right, so let's get into the black holes. Remember, of course, we discussed the 4 million solar mass black hole at the center of the Milky Way a couple of chapters ago, and it turns out that, of course, all galaxies that we can measure, so there are some galaxies that are so far away that we cannot actually see the stars going, in orbit around the center of the galaxy. In other words, it's hard to tell if there's a black hole in those galaxies or not. But all indications are that every galaxy has a supermassive black hole at the center. In fact, we think now, and we're going to get to this, is we think that this is really involved in galactic evolution. That the supermassive black hole forms very small at first, and then accumulates more and more matter. Basically has more and more of a fuel source. And anyhow, we'll get into that. All right. So this is a galaxy. We're looking in the radio region. Of course, the 21 centimeter wavelength is really important to astronomers. Don't forget that. That has to do with neutral hydrogen flipping. When the electron in neutral hydrogen flips from a spin up to a spin down, it releases a photon of wavelength 21 centimeters. That's in the radio region. All right, so this, we find that with some of the these nearby galaxies, relatively nearby anyway, we can actually measure how fast, the stars are going around, and as soon as you get orbital information, you can figure out what the mass is that they're orbiting, which turns out to be millions of times the mass of the sun, and in some galaxies, and not necessarily this one, but in some galaxies, billions of times the mass of the sun. Right, so those are the supermassive black holes, and like this one right here, M87. Remember, that is the nearest active galaxy to the Milky Way. That has a very massive, a supermassive black hole. Billions of times the mass of our sun at the center, and in fact, I think I might have mentioned this already, but if I haven't, let me re-emphasize it or talk about it for the first time. There's a thing called a telescope. Well, it's multiple telescopes, but together, these radio telescopes are basically the size of the Earth, and they have actually, these radio telescopes have basically looked at the center of M87, really looked at taken the first picture of the accretion disk around this supermassive black hole, and so that was actually quite a feat of engineering and technology to actually be able to measure that. All right. Anyhow, notice what this graph is telling us is there seems to be a linear relationship between the mass of the supermassive black hole at the center of galaxies and their size. Right. So there seems to be a direct relationship between the size of the galaxy and the size of the supermassive black hole. I mean, it doesn't seem that surprising that those two things would be linked, but it's good to, of course, you might think that it was already that way, but to actually see, evidence experimental evidence that shows that there's this linear relationship is, of course, very important in science. You always have to measure things and see if your ideas are correct. Let's see. These visible and X-ray images show so this is two supermassive black holes orbiting each other. We do think that sometimes during galactic mergers, these things will come together, and this, in fact, is kind of remember it's fuzzy, not because it's not in the visible part of the spectrum. This is usually either in the radio or in the X-ray. Anyhow, I guess this one is actually in the visible part of the spectrum. What's going on here is we think that the two supermassive black holes will eventually merge. Looking at the speed at which they're approaching each other, this particular situation, it's going to be another 400 million years before they merge. But this is something that takes place, okay? And we have to be able to account for these kind of things. So quasars are, as we mentioned before, these are the third of the AGN's active galactic nuclei, or the active galaxies, right? The active galaxies are extremely energetic, like way more energetic than the normal, quote, normal galaxies like the Milky Way and Andromeda. And of course, remember, these active galaxies are producing non-stellar radiation, or sometimes it's called thermal radiation, non-thermal radiation, where there's no black body curve to describe the energy that's coming from this. It's just, this really high energy source. Let's see, quasars are shown at distance. These, of course, quasars, of course, existed a long, long time ago. The age of quasars, if you will, was about 10 billion years ago. We really don't find many quasars any closer than about 10 billion light years. Let's see. And so when these quasars were originally viewed in the 1960s, remember that the name comes from quasi-stellar radio source. They didn't know whether they were part of our Milky Way with moving really, really fast because they had really large redshifts, or are they individual stars, or are they in fact galaxies really, really far away? And it turns out that this is the nucleus of galaxies, because when a quasar alters when the light changes, and it does change. It doesn't take very long for the light to change. Remember, the amount of time it takes for the light to change is an indication of the size of objects. And so these quasars, I think some of the larger ones take about a light month to change. So they're no bigger than about a light month across. So in general, they're much, much smaller than that. So these are relatively tiny objects, and so recently, with the Hubble Space Telescope, we've actually been able to see the host galaxy around these quasars. Remember, in the last chapter, the quasars, of course, are these supermassive black holes, and there's an accretion disk of matter that is heating up, and really that's the source of the energy, right? It comes from the accretion disk around the supermassive black hole. All right. This is kind of what I was just mentioning. The end of the quasar epoch occurred about 10 billion years ago. Quasars are generally older than that. Let's see. So what happens, right? You got these quasars. They're still, the black hole that was inside of these things is still there. So what's going on? I mean, why isn't it in the present day, or just a few tens tens of mega light years away. Why is it that we don't see any of these quasars? What happened to them? We certainly know that the black hole is still there. So this is actually some of this is very speculative. I want everybody to understand this. These next sections are especially this next section is speculative, although there is a lot of evidence that supports it. Okay, so remember, one of the things that we discussed is when two spiral galaxies that are roughly the same size come together, there is this incredible amount of star formation that takes place, right? Those are the starburster galaxies, and what happens after that, after this incredible star formation, is it leaves an object that is, that is, an active galaxy, basically. This thing is producing these two galaxies have come together. Their supermassive black holes at the center merge, and of course, what happens in that particular case? This would be like a radio galaxy, right? When we talked about the radio galaxies, these active galaxies. They're always elliptical, and they always have these jets of material that are coming off of it, because, of course, there is this tremendous amount of matter in the accretion disk, and the accretion disk, the black hole at the center has an incredibly strong magnetic field, and the charged particles follow the magnetic field line. So there's huge amounts of energy, but both matter and electromagnetic energy coming from these things. So when the idea here is it's really a basic, basically, this similar idea of what happens to stars, right? Stars, of course, will eventually run out of their fuel supply, and what we think is active galaxies. So this would be a radio galaxy. Will eventually, this is an elliptical that's come. Two spirals came together, formed this elliptical, and you're seeing. Sometimes we see these situations where we see the aftermath of this, where it's still an active galaxy, but then after time, that galaxy will eventually become just a normal elliptical galaxy, where it's not producing tremendous amounts of energy, non-stellar energy. It's just a regular old elliptical galaxy. Now we don't see, of course, we don't have the time to look and see an active galaxy becoming a normal galaxy, or one of these radio galaxies, which are also called blazars. By the way, these radio galaxies sometimes are called blazars because of these jets. I just wanted to mention that. And then, of course, we have when a spiral galaxy encounters a smaller galaxy, and there's a galactic merger. So what you have with that is you have a more massive spiral galaxy. In fact, that's a spiral galaxy that is producing tremendous amounts of energy, and that's what we call the Seyfert galaxies. The Seyfert galaxies are always spiral. They are active, of course, because they're active galactic nuclei, just like a radio galaxy has an active galactic nuclei. But of course, with the radio galaxy, you have these lobes. With the spiral galaxy, you have the energy is primarily coming from the nucleus, the AGN, active galactic nucleus, and then what the idea is that eventually the fuel source, the amount of matter that's in the accretion disk will eventually fall into the black hole, and it won't be supplied. You won't get as much material as during the Seyfert time, or during for radio galaxies or blazars. Oh, it says it right there. Look at that. Anyhow. Eventually they're going to run out of the fuel supply and just turn into a normal elliptical, or in the case of a Seyfert, a normal spiral. All right, so that's what's going to happen. Now we're going to look at the university in a large-scale structure that is clusters of